Okay, today we're going to look at Euler's form of a complex number. It's a beautiful form that connects together exponentials, trigonometry, and complex numbers, and is considered one of the most beautiful connections in mathematics. So we'll start by noticing that this was done by a guy named Leonhard Euler. He did it in 1748, which is a while back. But he did it, interestingly, at a time that was well before the Argand plane. You may remember that the Argand plane was developed by a guy named Jean-Robert Argand, and he did this in 1813. So when Euler did this development, he didn't have, or at least it wasn't known that he had, the tool that we're going to be using, which is to visualize some of this in an Argand plane. Let's go back and remember what that was. What Argand did was he took he made a modified Cartesian plane by representing real numbers on the horizontal axis and the imaginary part of a number on a vertical axis. And in this way, he was able to represent a number like 3 plus 4i, which is a complex number, as 3 in the real direction plus 4i in the imaginary axis, and literally create that complex number as a sum of kind of two vectors, a 3 of a real vector and 4i being imaginary, and ended up with the result, this round line of 3 plus 4i. And what he was able to do, and what this introduces, the idea that a complex number can be thought of as a magnitude, the brown here, which would be a magnitude of 5, and an angle. This angle here would be 0.93 radians, more or less. And we can think, therefore, of complex numbers in polar terms as a magnitude and an angle. What we're really doing is thinking of complex numbers as a real number that has been kind of rotated off of the real number line. When we jump away from the real number line, one of the ways to think about this is that back before we had complex numbers, we just had real numbers, and they had one of two directions. They could either be positive or they could be negative. But if we think of complex numbers as numbers with an arbitrary direction, and then we can kind of think of them as if we jump off of the real number line and step out into the imaginary plane, we do that by a rotation off of the real number line, and we get this new kind of number that's called complex, and it has an imaginary part, right? It has some imagination involved in jumping off those real numbers, and we can think of it as a magnitude plus a rotation off of the real number line. There's an interesting connection here if we think of and take a look at the idea of e raised to the I. So before we look at that, let's go back and remember what the definition of e to the a is. E to some number a is defined as the limit as n goes to infinity of 1 plus a over n raised to the n. And as n gets really big, this number will tend towards the number e to the a. So if we think about that from in terms of the imaginary world and consider e to the I, then e to the I is the limit as n goes to infinity of 1 plus I over n to the n. And what I want to do next is take a look at what this number does as we start from n equals 1, and just look at n equals 1, and then as n gets bigger and bigger, what does e to the I do? So we're going to zoom into this complex plane here and look at this part where we have, I've put a dotted line where the unit circle is at a radius of 1 from the origin. And start by taking a look at what happens when n is 1. What is 1 plus I over 1 to the 1? Right? When we put I equals 1 in here, we get a number, a complex number that is simply 1 plus I. And that number, we go over here to 1, and we go up to I, and we get a number that has an angle of 0.79 radians, which happens to be 45 degrees, right, or pi over 4. And it has a magnitude of root 2. And we have this number z1. If we then start changing n and increasing it, we're going to see this number move and eventually end up at e to the I. So let's look at z2. If we put 2 in for n, we get I over 2 and square it, and we end up by doing a binomial expansion here of 0.75 plus I, and we move from this point here, which was the original when n was equal to 1, we move to z2, which is this point here. Let's keep going. Let's look at 1 plus I over 3 cubed. And again, using the binomial expansion, or actually using GeoGebra, I let it calculate the real and imaginary components, and I get 0.67 plus 0.96 I, which is, now you'll notice it's starting to drop down in the imaginary component, and the real component is getting smaller as well. Let's keep going. Z sub 4, which is 1 plus I over 4 to the 4th, and we're going to see another movement here. It gets a little bit farther to the left, a little less real, a little less imaginary. Let's jump a little faster. Let's look at the 8th number in the sequence, 1 plus I over 8 to the 8th. And now we see that it's moving down this way. And here's z sub 16. If we put a 16 in, I over 16 to the 16th, we get 0.56 plus 0.87 I. And you'll see the pattern, what it's doing, what this number is doing is moving this way. And so let's just jack it way up. Here's the 301st value of n. If we put 301 in for n, this number is tending toward a location on the unit circle, which is 1 unit away from the origin, and also just happens to land at 1 radian along the unit circle. So e to the I ends up representing a rotation off of the real axis by 1 radian. And it lands us at this place, 0.54 plus 0.84 I. But what's more interesting about it is looking at it from the polar perspective, because where it lands you is at cosine of 1 radian plus I sine of 1 radian, or that could also be written as cis of 1. So e to the I is cis of 1, and it lands us right there. Well, that's very interesting, because now if we decide to say, oh, what would e to the 0.5 I look like? Well, we do the same thing, and I just decided to throw in the number 100 for n, just because that's an approximation. This is not exactly e to the I, by the way. It's just close because we haven't let n go all the way to infinity. But down here now, we're going to just let n be 100 and see where that lands us. And sure enough, it lands us again on the unit circle. As this 100 goes to infinity, it's going to be exactly on the unit circle. And now it's rotated up a half a radian. So e to the I times 0.5 has the effect of rotating a point off this real axis by a half a radian. And in fact, that's true for any angle theta. If we take e to the I theta, what we're doing is rotating a number from the real axis into the imaginary plane by an angle of theta radians. So e to the I theta is just cis theta. And this leads us to a couple of really beautiful results, of course. And the first one is, well, what would e to the I times pi over 2 be? Well, that means we're going to rotate off the real axis by pi over 2 radians. We're going to land up here, and this will give us cis of pi over 2. And cis of pi over 2 is simply I. There's no real part, there's just the imaginary part, I. Now, of course, you can imagine that this gets a little extended if we add some modulus to this, some magnitude. Everything I've done so far has a magnitude of 1, but we can simply put an r in front of this here and an r in front of this, and we get Euler's form of an arbitrary complex number, which is r e to the I theta, has a magnitude of r, and it's rotated into the imaginary plane by an angle of theta. It's the same as r cis theta, and it's really a wonderful thing. Now, the other interesting one that's very famous is if we take e to the I pi, and what that does is it starts us here at 1, because we have a magnitude of 1, and rotates us by pi radians all the way over to the other side of the real axis and lands us at -1. And you may have seen this before. E to the I pi is -1. This is y. So we're going to go back now and look at some of the properties of cis, but we're going to look at them from the point of view of Euler's form. For example, we know that cis of theta times cis of phi is equal to cis of theta plus phi. Well, in Euler form, this is simply a representation of the rules of exponents, because cis of theta is cis of theta is, well, in exponent form, this is simply e to the I theta times e to the I phi, and we're just going to use the rules of exponents. When you multiply exponents, you add their when you multiply powers, you add their exponents. So we get e to the I theta plus I phi, and we can factor out the I, and we get e to the I theta plus phi. So here's a very simple way of proving and deriving new formulas involving complex numbers, because we're really just using the rules of exponents. It's really sweet. So let's do a couple of practice problems. We're going to evaluate a couple of things here. Let's start with e to the minus I pi over 4. Well, e to the minus I pi over 4, well, that's just cis pi over 4, or we can actually really just draw it, right? Minus pi over 4 is down here, and so if we want to, we know what the coordinates of this are, because we've got the x coordinate is cosine of pi over 4, which is, or of minus pi over 4, which is 1 over root 2, and the imaginary component is negative, and that's the sine, so we just get 1 over, the coordinates of this are 1 over root 2 and minus 1 over root 2. This is the imaginary part. And so as a complex number, then in a plus bi form, this e to the minus I pi over 4 is just 1 over root 2 minus 1 over root 2 I. And that's all there is to it. For part B, let's look at I to the minus I. Well, if you think about what I is, let's look at that. I is e to the I pi over 2. We saw that before. E to the I pi over 2. And if we raise that, this is just I, raise this to the minus I, then by the properties of exponents, this is e to the minus I squared, right? Minus I squared is this I times that I with the minus sign, times pi over 2. And minus I squared is 1. So this is just e to the pi over 2, which is a real number. Oh, that's interesting. A real number, I to the minus I, is a real number, e to the pi over 2. Okay, let's do something else. Let's use Euler's form to find the square root of I in Cartesian form. And then we're going to confirm that the result is correct by squaring the Cartesian form and see what we get. So what is the square root of I? Let's get rid of this stuff and we'll do it up here where I have a little bit more space. Okay, so what we want is the square root of I. So the square root of I is just I to the 1/2. And we said that I, remember, I is e to the I pi over 2. And if we take that, take I and take the square root of it, we get e to the I pi over 4, which is, so this is the square root of I, which is cis of pi over 4. And if we think about where that is, cis of pi over 4 is here, and it has coordinates of 1 over root 2, 1 over root 2, plus 1 over root 2 I. So that should be the square root of I. Well, let's see if it is. Okay, so we're going to confirm this result by taking 1 over root 2 plus 1 over root 2 I and squaring that and see if we in fact get I. Is I equal to this? We'll find out. So when we square this, we get the first thing squared, the first term squared, which is 1/2, plus twice the second term times the first term, twice the product of the two terms. So that's 2 times 1 over root 2 times root 2 is 2, and an I there, plus the last term squared, this squared, and that's 1 over 2 I squared. Okay, so let's look at this. This is 1/2. Let's simplify a little bit. Plus this 2 and this 1/2 cancel. We just get I, and I squared is -1, so we get minus 1/2 for that. Oh, and look what happens. The 1/2 and the minus 1/2 cancel, and we just get I as we expected. So here is the square root of I. 1 over root 2 plus 1 over root 2 I. I should point out that on your calculator, the syntax for using polar mode when you're using either cis or EulerForm is the EulerForm. So you can't put cis in your polar form in your calculator. You can put r e to the I theta, but be sure that you recognize that theta is going to be an angle in radians, even if your calculator is in degrees. Okay, even if your calculator is in degrees, you need to put this angle as radians if you're going to work with this polar mode. Alrighty, so here's a little bit of homework for you to do. Take a look at those problems, see where you go, and we'll pick it up next time.